Okay, my friends, today is going to be a very interesting day. This is Roger, Mudfossil University. I am going to try to explain quantum entanglement, dipole molecular moments, and the atomic theory called electron flood. Now, when I say quantum entanglement, yeah, everybody's heard that. Whoa, what does it mean? Got any idea? No. Nobody knows. They say, oh, well, you push a thing over here and somewhere over across the other side of the universe, a butterfly moves or something like that. Well, everything is pushed up against everything else. Absolutely. You push any molecule here, something's going to happen, but eventually it will damp down to where there is virtually no effect on its neighbor at some point. However, when you take these gauge blocks that are extremely finely machined, they are flat as a pancake. They're used in calibrations. That's why they have these like 7/10ths of an inch, that type of thing. Now, if you take these two blocks together and you put them together at a 90-degree angle and then you twist them together, what you really do is lock the electrons into the electrons of the other part that you have mated it to. Because there is nothing in the universe, a zero, that consists of only a positive surface. Everything is coated with electrons, painted with electrons, painted with electrons. Everything is painted with electrons because the nucleus will always be flooded with electrons, which are the negatives. So, negative to negative, we're locking them together. You watch what he does. Now, I've done this myself, and I know exactly how it works. And it is, you have to snap them and crack them apart to get them apart. You will never be able to pull them apart because they are literally one piece when this is done.
Together. The thing is, nobody is certain about how they stick together. There are several potential explanations that most likely work together to create the effect. First of all, because there is nearly no air between the smooth surfaces when pushed tightly together.
Yes, that is extremely important because the electrons have to be face to face with the other electrons. You can't have any gaps and voids.
The air pressure might push in on both blocks.
It has nothing to do with the air
the surface
pressure.
tension from oil and water vapor on both blocks might hold.
There is no surface tension of oil and water. They have to be extremely clean. Well, for some reason, this thing buffering today, and it never does that. All right, started buffering there for a second. I don't know why. Here we go.
Second of all, the surface tension from oil and water vapor on both blocks might hold them together. Finally, intermolecular forces might cause attraction since the surfaces are so smooth and the molecules from the blocks are in such proximity.
That is the reason. It has nothing to do with surface tensions and this and that of water and oils. They have to be just as clean can be. When you put those at the 90 degree and then you just twist them, you're twisting just like that. You're twisting one right into the other like Velcro. And if you know Velcro, if you take it and you jiggle it when you put it, the two Velcro pieces together, it will hold much harder because it's entangling itself. When you push them together, you might catch a little of this. When you push it together and jiggle it, you got all kinds of entanglement. And that's what's happening here. That is quantum entanglement. I could show you more with toys than you will ever learn at CERN. Okay, now, we just saw quantum entanglement, which is where molecules interlace with other molecules and they entangle their orbital electrons. Okay, now, that's quantum entanglement. This is water, H2, the two H's, O is the oxygen. Now, there's something that's called a dipole moment. And what's a dipole? Now, a dipole just means you have, like a bar magnet, you have a negative side and you have a positive side. And you say, why is this negative and positive? Well, here's the deal. Once you hit the second level of orbital, it's called the it's called the p orbital. You have the s orbital down in the real bottom, way down inside, and there's only 2 electrons. But then you get out in an area where it's called a rule of 8, and you need 8 electrons to make a stable atom. Oxygen only has 8 electrons altogether, and 2 of them are way down deep, like I said, in that s orbital. And then these 6 are up in the next orbital, but it needs 8. So that's called oxidation. It needs to hook up with somebody that's got a couple extra electrons. So who's got that? Hydrogen, each one of them has 1 electron. It says, well, I'll share with you. It's okay, I'll share with you. So they share their electrons. So now we have 2, 4, 6, 8. However, that means that the oxygen has accepted extra electrons, so it becomes primarily negative, because that's what electrons are, and the hydrogen has given up its electrons. So its region becomes primarily positive, and it's out here. Now, here is the key. Think about this very carefully. You see that brown ring there? That is the zone of influence that this molecule or this atom has. Way out here. And you don't see anything out here. You're looking, you see them. If you're looking in a microscope, you might be able to, they have some new electron microscopes that can actually see electrons in orbital, I believe. But forget that. What you have is not enough electrons. You need electrons. That makes it negative. That leaves this in a positive state. This is a bar magnet. So the next time another water molecule comes up here, this side is going to attach to here. All right, and then you get chains of water, makes a the surface tension on a water. Now, this is the dipole moment. You could actually figure out, and I have done this, and I'm going to show you I did. I'm not bragging, but I just want to show you because this is, I'm pretty intimate with this stuff. I'm not just guessing. So there's going to be a distance that electron will sit away from the nucleus. And it's not going to be the same as these are because it's being pulled away. So this comes into our solar system. Think about this now very carefully. These electrons are able to be pulled in more tightly to that positive attractive source than these electrons, because these are already being attracted out this way. We're trying to pull them in this way, but they are going to be a further distance out than these because they are being attracted this way. So if this was light, which it could be, that light would arrive here later than this light. Okay? Think about this carefully. This light out here is really being pulled towards these positives because this is negatives. So it will not get to that oxygen because it's already pulled this way. It's not going to have the same pull as these electrons to the core. Critical in electron flooding. Now you might have to go over this 2-3 times to focus in on what I'm telling you, but this is the region that this owns, just like our solar system owns a region. And we may overlap with some other solar systems, obviously, because their sun controls a huge region too. Some suns are not going to be these little bitty things. They're going to be huge, and they're going to come way into our solar system. Some suns are going to be little tiny, and they're going to barely invade our solar system. And I will show you my little Wile E. Coyote diagram on that in a moment. But this is a molecule of water. This is the dipole moment, which is the separation of charges. This is a polar molecule. And it doesn't matter whether you have covalent or ionized bonding. It doesn't matter. Anytime they are together and they are locked in an embrace, you're going to have a positive and a negative somewhere. All right? Because they're hooked together. So I'm sharing with you, you're sharing with me. If I'm taking your electrons, I'm going to become more negative. If I'm giving you electrons, or you understand, if you're taking them, you're going to have more negative. If you're giving them up, you're going to be less negative, so that becomes more positive. All right, so I hope that didn't confuse you too much, but that is the nature of molecules. Now, I said I did this stuff, and I did. And this is right here. And we're going to go into the Millikan oil drop in a second, because that is absolutely critical to understand this. Now, I did this, well, you can see the paper. It was a while ago. Hold on a second. I can't see the whole thing at once. But anyway, I mean, I calculated all this stuff out. This is how much, I didn't take anybody's word for this. I went through what Millikan did, and I figured out what he did. And I can't really remember if I thought he was right or not. But I can tell you what right now. I honestly believe right now, if you did Millikan's oil drop experiment, you're not going to get the 1.6 times 10 to the minus 19 or whatever it is 1 electron volt. It will be different because the Earth's literal size since 1909 has increased. I am almost 100% sure of that. And if the Earth's literal size increases, that means its literal pull increases. That means the Millikan oil drop experiment will require an increase in voltage to push that electron off. We're going to look at that in a minute. But anyway, you could see I did this a lot. I mean, and then I did the thermochemistry of it too. What happens? How does it give up electrons and take them on? Because pH is dependent on the temperature. People don't understand. That's hydrogen protonization is pH, and hydrogen protonization happens when you get more and more or less and less of electrons. That's all it is. That's heat and cold is nothing more than pushing electrons in and pulling them out. And I'm going to tell you something right now. Freezing temperature is nothing more than pulling electrons out until the point at 32 degrees there is no electrons left. It crystallizes. All right. I actually did Millikan's oil drop experiment and calculated out all the energies and all this business. Now, this is what it says about Millikan's oil drop experiment. And believe it or not, in 1909, when he did this, he found out how much electricity, how much push of negativeness it takes to push an electron and keep it suspended in air so it does not come down, which means it voids its gravitational influence. He calculated out every electron is sucked to the Earth with 1 electron volt. That is gravity. And I'm going to show you about gravity, because there's nothing more than magnetism. The Earth is a positive attractive force. Every electron is pulled to Earth, and every single thing there is flooded with electrons. Nothing there exists without electrons. Now, that brings up a point. I say everything with electrons is pulled to Earth, and I will show that in a second in experiments. However, if you don't have enough electrons to overcome the positiveness of your core, you'll float up in the air, because then your core will become positive. If the Earth is positive, you go up in the air. Guess what that is? What goes up in the air? Hydrogen. What does it do? It only has 1 electron. It's not enough. It's got more positiveness than it has negativeness to be pulled to the Earth. Right? There's a certain attractiveness of the Earth, and hydrogen doesn't have enough negativeness to come to that positiveness. So, neither does helium. But helium doesn't lift like hydrogen because it has more electrons to be attracted to Earth, just not enough. And then you go into lithium. Hold on one second. Hold on, I'm getting there. Ah, here it is. You see this? Hydrogen has 1, helium has 2, then we get to lithium has 3. Well, guess what? Lithium just barely comes to the ground. Why? Because it's jumped from the lowest orbital. There's only 2 electrons in the first s orbital. Then you go into your 8 orbital electrons, and that's the first one in the 8 orbital. See, 2, 4, 6, 8. So your s orbital, and then you go into your p orbital, which has to have 8, and then all the rest of them have to have at least 8 in their outside orbital to become stable. All right, so remember that. All right, so here goes Millikan's oil drop experiment. And he is dropping one single electron and is calculating how much electricity or how much negative potential to push that electron into stability in floating. So listen to what it says here. I set you up for it. Here goes.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter.
All that means is he's adding an electron or a bunch of electrons to these neutral oil drops. Once he adds the electrons, he's figuring out how much it takes to push that chunk of stuff back up in the air. It might have 1 extra electron, 10, 20, 30. It doesn't matter because when he divided it out, it came out to always one certain number. I mean, he might have had it divided by 20 or 30 or 40 or 50, but it's still going to come to that one single number. So he knows that one single number is going to be that one single electron volt. So here goes. I hope that explains it, but probably not.
Charges produced by the X-rays attach to an oil droplet, producing 1 or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage
That's called gravity.
is applied, the droplets that have a negative charge will fall more slowly.
All right, the droplets that have a negative charge are the droplets that he charged with that electron beam, X-ray beam.
Stop falling, or even rise.
All right, they have put the potential on the bottom plate to be, instead of positive, which the Earth is, they turned it negative, which pushed against the negativeness of the extra electron and is pushing it up in the air. And then eventually it would just hang flat in the air, and that's when he calculated out how much voltage it took, and then he divided that voltage by this one huge gigantic negative number, and it came out to the same number every single time in multiples, 1 or 17 or 22 or 15 or 9 or whatever it was, but it was always a multiple of that number. So there was, I can go along with his conclusion that is how much voltage it takes to push one electron up in the air. Let's finish it, and let me come back a little bit and hope this makes sense, because this is a little over the top for most people. But it's really not that hard if you just sort of say, they try to confuse me by making it confusing. It's not confusing. It's not confusing. All right, here goes.
And the viscosity of air through which they fall.
Gravity.
When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise,
because they're pushing up.
depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs.
All right. That's what's called 1 electron volt. Now, my electron flood theory says that all atoms in their core are made of multiple particles, not just protons and neutrons. Every proton stabilizes only when it hits exactly 1,836 little bitty particles. And half of them are going to be positive and half of them are going to be negative. That's what a proton is. That's what a proton is. It's basically a neutral particle. There's always extra neutrons, which is a negative particle. A neutron is not neutral. Neutrons are negative, and the core of a hydrogen atom is a neutron. That means it's a proton, which they say is only in there, and they don't even think of the electrons even as having weight, to be perfectly honest with you. What they do, and I've calculated it out, it's 0.005485, something like that. It's right. It's 0.005485 something, right in that area. Now, that's your hydrogen proton, but not only that, it has one additional electron that attaches there. Now, what does that mean? This core will become negative and no more electrons will be allowed because it already has an extra electron. So another one will come in here and they'll say, hey guys, can I come in? And then it's going to say, no, no, we already got one extra guy. Because if you take the weight of a proton, of the nucleus of the hydrogen, it doesn't weigh one proton. It weighs one proton plus one electron. And they know this. I don't know how they can just wash it off the edge. And then there's an additional electron in orbit out here. It can't get there. It's trying, but there's a pushback. And I'm going to show you a little toy that will demonstrate that elegantly. Okay, this is Latham's Crazy Machine. It's fabulous. I've shown it a million times. And he's going to show you how to build an atom. That is a brass core. It has a bunch of negative magnets around it, and he's going to introduce a positive core in the center, which is called electron flooding, which is the nature of everything in our universe. Now, there it is. Boom, you see it? It's solid. That's the positive. He's going to put that inside that core. And now you have an electron-flooded nuclear core. When another electron passes by, it does that. Quantum mechanics. That is the quantum deal. Now, you have the nuclear-flooded, electron-flooded core. Depending upon the quantity and the intensity of the core, it depends on how many electrons flood it, and how many electrons flood it. It will decide on how many electrons will be in orbit. The bigger the core, the bigger the flood, the bigger the flood, the bigger the orbits. Simple as that. When you take these molecules, or these are atoms, when you take those and you add them to other atoms, you get the quantum entanglement of these particles in their core, in their shells. Some of them will be here and some will be here, but some of them will be attached to both particles at the same time. That's what we're going to look at next. Let me just do this before we do, though. There's another thing that can happen to all molecules. They can heat. What happens when they heat? This is what happens right here. They start to shake. All right, you see them shake and shake and shake. What is this really happening? There's other electrons coming in and banging and banging and banging. And electrons coming in is heat. Heat is pH. pH is protonated hydrogen. That means the electrons are flooding through there. They're moving, they're boiling, they're forcing things out of their way. All right? So, that's heat, shaking like that. Vibration, sound, Boom, when it took off just like that, that was light. All right, boom, there it goes. That's light. Once it gets away, it's light. Now, it would normally just go right off like that until it collides with something and it absorbs that collision. It's all it is collisions. Now, you're not colliding that particle, though. As you saw, it has a field surrounding it. It can't hit certain things. And the things that it won't hit is other electrons. And every single thing there is that it collides with will be an electron. Because there is nothing that is not coated with electrons. It really boils down to quite simple mechanical situation. You have two basketballs, one here and another one, whatever it bangs into, because it's going to be a basketball. Boom, they go like that. And when they do that, they bang together, they luminesce. They are luminescent fields. Just happens. That I cannot explain at this moment. Although I'm going to show you another toy that I think might explain it. I'm telling you, it's amazing. Toys are so perfect for physics. Anyway, here goes. Just in case you feel there might be some doubt as to whether light can be sped up, there is no question whatsoever. That is light from a red laser. That is light being sped up because it's being forced to exceed its normal speed because of the Venturi effect. These are the Higgs bosons, and then the Higgs fields that present on the tip of them. This is a new particle nobody has any clue about. These are the torus little fields that I'm going to show you right now. That the only thing I can think of is they get smashed like that, crushed, and then they emit spikes up and down in some kind of energy. This shows a wider expanse here, and then, whoops. And then you can see it's expanded and then it's contracted up here. That means it's obviously slowing. These are the things you can see, maybe a little spike there. But this is the torus that I think may have something to do with it. All right, it's called a toroflux. It's a nice little toy. And I'm going to let him show you what it's
Introducing the amazing Toroflux, a tactile toy made from a single band of metal. Think of it as a slinky in the fourth dimension. Toroflux's spiraling band loops back on itself.
All right, there's your torus. Going down the torus. Now, when you crush this, somehow, you're invading this field's region. And it's somehow forcing like a tension in the inner torus. That's all I can say. That's just a guess. Nobody can tell you why anything luminesces. It just does. And it's from a concussion. That is as far as I can get to. Okay, I'm sure we went over this, where the oxygen and the hydrogens are entangled with their electronic orbitals. Right? So that means this is pulling this way, this is pulling this way, so that is going to be stretched. These are going to be tighter up against. So if this was light, the light would be coming strongly this way, and it would be coming less strongly this way. That I'm pretty sure of. So if we have these entangled molecules, what would we have if we looked at our solar system in relation to the rest of the universe? Well, here's our sun, and here's our little planets running all around our solar system. And this is the sphere of influence that the sun controls, because I say, and everything says, that is a system, the center being the pull, which is the nucleus. Right? And everything is pulled towards it and staying in its orbitals, for the most case. Now, my contention is that we only understand our solar system, and not even that well. So if there was another star off to here, which they're all over the place. They say, oh, this one's 3 million light years away, and that's this so many light years and all this business. Well, let me tell you something. at this point, if light can be sped up and slowed down, which it absolutely can be, and it is a magnetic particle, which it absolutely is, a strong magnetic pull this way will keep that particle from coming as fast as what we call the speed of light. It will be redshifted because it slows. Not because that thing's shooting away from us. And that's what they came up with. Hubble and Einstein just made a terrible mistake. It's a terrible mistake. The speed of light can speed up and slow down. And the only reason it's consistent on Earth is because Earth sucks that electron down. 1 electron a volt per electron. And every single thing there is loaded with electrons. The more electrons, the heavier it is, the harder it smacks to Earth. It's just as simple as that. And that's why hydrogen floats up in the air. It doesn't have enough electrons. You got to get outside that deep 2-particle orbital, which is the inside s orbital. You got to get out to the 8 region, and then it's heavy enough where it's attracted to us. So what does that mean? Let's say we got a huge star over here somewhere, really digging into our solar system and letting these particles not come fast. It's really dragging them back, saying, all right, I'm going to shoot you out of here, but I'm going to hold on loosely, but I'm not going to let go. There's a song about that. All right, so it's going to hold on loosely, but it will never let go until it finally escapes into that range. Once it's out of here, it's out of the influence of here. However, at this point, it's already extremely redshifted. So we're going to see the light in a shift, and we're going to say, oh, that thing's flying away from us because light cannot slow down. Well, it absolutely can slow down. And it will slow down hardly at all from this one, and it will slow down a little less here, or a little more from this one, and so forth, depending upon their infringing of our dipole region. We own this region. They want to come in and take it. They want to be part of us. And when they are, they're not going to let their stuff come in just as easy as it's supposed to, or we think it's coming in. So the bottom line is, let's discuss this according to what Einstein had to say. And of course Hubble, and all of them took their marching orders from Einstein. So here's what we got. Light speed is constant. Albert Einstein said it cannot happen any other way. It goes exactly a certain speed. It's the constant. Well, 100% of energy and space and atomic theory is based on that foundation. That is the foundation. Everything's based on that foundation. Once you lose that foundation, everything is now in doubt. And some things are not in doubt whatsoever, is the ability to speed up and slow down light. No question whatsoever.